Dear learners, welcome back to NPTEL online certification course on novel drug delivery systems. I am Dr. Satish Davanapelli, working as an assistant professor at Department of Pharmaceutical Sciences and Technology, Institute of Chemical Technology, Mumbai. So, in our first week, we are discussing on the introduction to novel drug delivery systems. So far, we have discussed what are the novel drug delivery systems, how this system can be utilized in pharmaceutical applications, and then we have seen the polymers used in the drug delivery systems, and so far we learned on the various properties of the polymers, the classification of the polymers and the nature of the polymers. And we also seen the applications of the polymers in drug delivery systems. In our previous lecture, we have discussed on the temperature sensitive polymers, and we have discussed various example on the pH responsive polymers, and further we have seen the glucose responsive polymers which we can use for the various diabetic applications, and also we have seen the light responsive polymers, and then we also seen enzyme responsive polymers for drug delivery applications. So, today we are going to discuss on the various examples of the most commonly used polymers in drug delivery systems. So, here we are going to discuss on the most commonly used polymers in the drug delivery systems. We are going to see what are their nature and how they will respond in the body and how they will degrade in the body, and we will see some of the examples. So, as we know, these polymers we can utilize it and we can convert into the various drug delivery systems, either for implants and also for the as in a colloidal carrier systems. So, when you use polymers for implants, after encapsulating or loading of the drugs into the carriers or the implants, which undergo the various degradation mechanisms and which will control the release through dissolution or diffusion control systems or by the various types of the release mechanisms by swelling. So, which will slowly the drug will come out, and by using of these polymers we can also convert into various colloidal carrier systems. For example, polymeric nanoparticles, we can convert drugs into the polymeric nanocarrier systems by using the polymers, and which will comes in the range of 1 to 1000 nanometer, and we can use same formulation for even oral and other routes of administration based on their particle size. And we can use the polymers, we can convert into the micelles also. We can convert polymers into the dendrimers, as well as we can convert this into the polymerosomes. And not only that, we can use polymers and we can conjugate with various types of the drugs, which is called as polymer drug conjugates, and the response in the body of the free drug is completely different from the drug conjugations. Here we can use various types of the polymers with various types of the anti-cancer drugs. So, with that we can make a new product and which will shows completely different ADME profile and their efficacy and the safety is completely different compared with your free drug. So, not only this limited to the drugs, the same polymers like positive charged polymers like Chitosan, poly-L-lysine, which you can also use, you can convert your biological molecules like siRNA, DNA, which we can use and complex it and we can deliver for the intracellular drug delivery for gene delivery. If you would like to know more on this polymer drug conjugation, so this is my book chapter. So, you can go through, you will get lot of information on the polymer drug conjugations for cancer treatment. So, here we know that we use these polymers and we can make into various control release formulations. We can use polymers, you can make control release capsules, we can also convert into the various types of the control release tablets, and by using these polymers we can make micros or nanospheres which will also show the drug release in controlled manner. We can also use the polymer conjugated lipids which can also work as a various types of responsive liposomes. With that we can improve the surface properties by coating of the lipids with the polymers. We can also control the release, and we can also use these polymers for the microcapsules to protect from the various degradation parameters, and also we can use these polymers to make hydrogels and the nanofibers, and we can also make various films, especially oral thin films. So, that will disintegrate very fastly in the mouth, and also you can convert your bitter active drugs into the oral thin films which will mask the taste. So, these are the various applications of polymers. We can use it for the drug delivery applications. So, here in our previous class we have discussed on these various biodegradable polymers. We have seen the classification based on the nature and classification based on the biodegradability, and also we have seen the classification based on the stimuli responsive. So, here now we are going to see on the biodegradable polymers, which are natural polymers and the synthetic polymers. The list goes on and both have the advantages as well as disadvantages. So, these are the examples: chitosan, alginate, hyaluronic acid, dextran, gelatin, which are considered as a natural polymers. We use it in the drug delivery and tissue engineering applications. And these are the synthetic polymers: PLGA, polycaprolactone and polyvinyl acrylate, polyamino acids and the pluronics, which can also use in the drug delivery applications. So, here we are going to discuss on particular polymers and their properties and how they will work in the body. So, here first the most and the best commonly used polymer, it is a PLGA, polylactic-co-glycolic acid, which is biodegradable and the biocompatible copolymer. Now, remember this word when I am using copolymer, nothing but it is composed of lactic acid and the glycolic acid of the monomers. So, it contains two monomers, which is nothing but copolymers, and when you use these two together, still the polymer is biodegradable and the biocompatible, which is very important for any polymer which you want to use in the drug delivery application. With this, we can make various types of drug delivery systems and implants and the devices which can be also used in the tissue engineering applications. So, when you use these combinations of these monomers which are in market, these are available in various ratios, and that is very important for the polymer properties. So, here the third point, PLGA drug loading, encapsulation, release properties are significantly influenced by the molar ratio of lactic acid and the glycolic acid monomer used during the synthesis, because glycolic acid is the water soluble compared with the lactic acid. So, here when you use the high proportion of the lactic acid, it will undergo the various when you use 50-50% ratio, that is nothing but equal amount of lactic acid and the glycolic acid. So, the structure which will available in the amorphous form and which will degrade very fastly because of its hydrophilicity. When you use 50-50 ratio, the degradation will be very fast because of the hydrophilicity of the final copolymer is very high. Whereas, when you go for the increment in the lactic acid ratio, nothing but 75-25, 85-15 ratio. So, the polymer become more hydrophobic because of the high amount of lactic acid, that leads to the slower release. So, these properties are very important based on your application. So, if you want a control release polymer, you can go with this, and of course, the ratio will also influence the drug loading, encapsulation and the release properties. So, while doing the experiment, you need to optimize the right ratio for your active molecule. Based on that, you can select right ratio. Now, the degradation parameter also very important for this PLGA. So, PLGA undergo hydrolysis and it will break down to lactic acid and glycolic acid, and further it will metabolized and excreted. It completely undergo the biodegradation. These polymer we can use in various types of the novel drug delivery systems, and it is not limited to the drug delivery. People are using in the various biomedical and tissue engineering applications also. Now, the second polymer is very important, poly-N-isopropyl acrylamide. As we discussed in our previous lecture, we have studied the thermoresponsive polymers. There we have discussed on the temperature responsive polymers, which we can use it for the active targeting, especially in case of cancer, because cancer microenvironment is completely different from the normal cells. Because of the high metabolic rate, the internal or the temperature in the cancer cell will be very high. So, that condition is called as hyperthermia. So, such conditions, when you use these polymers, the response of the polymer is very important for the active targeting. So, these polymers will go and retain at that particular cancer cells which show high temperature compared to normal cells, and there your drug will release based on the temperature, because the response will happen the temperature more than in the normal cell temperature. So, in such cases, not only poly-N-isopropyl acrylamide, we have so many various types of the polymers which will respond to the temperature. Such polymers can be used and we can target to the cancer cells through active targeting. Now as we learn, these polymers will respond at a lower temperature which is called as LCST, that is the below 32 degrees centigrade. When you increase the temperature, your polymer undergo into the insoluble format. So now you can see here is the one best example which is published by the authors. So here you can see at the temperature of 25 degrees centigrade, the solution is very clear, that is soluble in medium at low temperature. When you increase the temperature from 25 to 45 degrees centigrade, now you see there is a change in their appearance. There is a physical change in the appearance which is required for a targeting systems. So poly N-isopropyl acrylamide, which is thermoresponsive polymer, when used for the biomedical application, it will respond at the target site. So these hydrogels can be used in the drug delivery systems and the tissue engineering and the smart coatings due to their thermal responsive properties. So this is also one of the most commonly used thermoresponsive polymers for the targeting. And the third one is we are going to see on polyamidoamine. So these polymers we specifically use in the dendrimer applications. As we know, so dendrimers are the tree-like structures which are 3D network structures. Now here in the 3D networks, we will see there is a internal core, and after that you will see the interior architectures, and further you will see their terminal groups. So which is the repetitive units, repetitive branch subunits of the amide and the amine functionality. So you can see this looks like a spear structure and it mimics like a spear, and which are able to form dendrimers compared with the other polymers. It looks like a tree-like structure. So with the functional groups which are amide and amine, we know that which are cationic in nature, that will give the positive charge which is helpful for the complexation with the negative charge molecules, especially nucleic acid and some are the proteins and the peptides and siRNA. So it will help for the complexation or stabilization of the biological molecules. And not only that, that positive charge will help to interact with the negatively charged phospholipid containing cell membranes. With this, we can improve the cell uptake by using the cationic or electrostatic interaction with the cell membrane. So already we have studied all this. We can see the polyamidoamine are the spear-like shape which are forms internal molecular architecture which looks like a tree-like branching, and with each outward layer or generation containing exponentially more branching points. So with this surface functional group you can conjugate with various types of the drug molecules. This polymer mostly we use in for the dendrimer applications. Now the fourth one is the Chitosan. As we know that this is the natural polymer and it is a biodegradable polymer and the biocompatible polymer which shows various types of the actions. It will show the antimicrobial application also. So this polymer is one of the mostly used polymer for the drug delivery and tissue engineering applications. Because of their properties and the positive charge, pH responsive, temperature responsive and the biodegradability, biocompatibility. So, this is one of the mostly used polymer from the natural polymer category, and this shows good absorption enhancing, and also it will show the control release, and it will help in the bioadhesive with the various mucous systems in the body. So, this polymer we can use it for the control release and for the permeability enhancement as well as for the mucoadhesive application. The degree of deacetylation of this chitosan and the derivatization with various side chains can be source of manipulation for specific drug delivery systems. So, if you increase the deacetylation of the chitosan, the solubility and their property and the molecular weight will also differ from the original chitosan. And by using various derivation or conjugation with various molecules, we can change the properties of the chitosan, we can convert into the pH sensitive and the temperature sensitive, and even stimuli various types of stimuli responsive polymers by using the chitosans. So, with this functionality we can use it for various applications. And here we will see the another one, that is a poloxamer. It is also known as pluronic. It comes in the market in various brand names. Pluronic F127 is a tri-black polymer. The PLGA is co-black polymer of lactic acid and glycolic acid, whereas pluronic is a tri-block polymer which contains polyethylene oxide, polypropylene oxide, and with the repeating unit of the polyethylene oxide. So, that is why it is called as tri-block copolymer, tri-block polymer. So, here this is non-ionic in nature. When you disperse in water, you will not see any charge in the solution, and it contains various number of repeating units, that is we have already discussed ethylene oxide, which is hydrophilic and the water loving. Now, you can see here the two methyl groups, and which is ethylene oxide, and the propylene oxide, which you can see 3 carbon atoms, and which is water repelling and hydrophobic properties. With this polymer we can say that it is amphiphilic. So, we can utilize for if your drug is amphiphilic and water insoluble, we can make micelles and other carrier systems also. So, this can be also used in the various drug delivery and the tissue engineering applications, and this polymer will also utilized as a stabilizer because of its low molecular weight, and also this polymer will work as a temperature sensitive polymers. When you want to make in situ gels, so this is one of the most commonly used type of the polymers in when you want to convert into in situ gels. In situ gels nothing but you will see the phase transition of your formulation from solution to gel at biological conditions, especially in the temperature. So, these are the further reading. You can go through all these various types of the this slide speaks about the further reading. So, here you can refer various references which you will learn the polymeric controlled drug delivery systems and also polymers used in the drug delivery and the selection and the role of polymers in the designing and drug carriers, and we can also read polymers in controlled release drug delivery systems. So, these are the various references. So, with this I am stopping today's lecture. In our upcoming classes, we are going to learn various types of the novel drug delivery systems and how we can use and where we can use such novel drug delivery systems to target the various types of the diseases. Thank you so much.